The objective of this video is to introduce basic tools for thermal analysis of semiconductor devices and heat sink selection. The idea is that when we have a semiconductor device and we're talking about either a diode or some type of transistor, a MOSFET, an IGBT, or a BJT, we have losses that occur within the semiconductor junction. And these losses will generate heat that must somehow be dissipated, or we risk damaging or melting our device. In some designs, you'll see that you can actually dissipate the heat from the semiconductor device without taking any type of cooling system design. While in other designs, you need to actually apply a heat sink or even a cold plate to it, a liquid-cooled cold plate, in order to extract enough heat to prevent your junction from overheating. So regardless of the device, we start with some kind of semiconductor junction. This is our PN junction of our MOSFET or diode or BJT and so on. And then this junction is placed inside some type of case. And so in the previous video, we talked about a TO220 package. That's one common case for semiconductor devices. Another case could be a TO247. But the point is that these are standard cases that allow us to interface a heatsink to the device. And oftentimes, our case is metallic, and it's connected to the drain of our MOSFET. So we typically need to isolate the case. So what we may do is we may place some kind of isolation pad here. For safety purposes, we oftentimes will not want to have our heatsink exposed to the voltage of our drain. So for example, if you're implementing a buck converter with a MOSFET on one side and a diode on the other side, you may not want the drain voltage of the MOSFET in contact with the heatsink, because if anything touches that heatsink, it could be exposed to a large voltage. So what we do is we purchase some kind of isolating pad, and then on the other side of this pad, we'll actually mount our heatsink. And I'm drawing kind of a cartoon figure here, but I want to show you some pictures of what these devices actually look like now. So you can now see some pictures of these devices, and starting from the top, we've got a MOSFET. This is a silicon carbide MOSFET, which is in a TO247 package. So we're showing the front side, and then the back side is here. And you can see that on the back side, our case has this metallic area, which is where you are intended to connect the heatsink. So it's metallic, so it's very thermally conductive. Heat transfers easily through it without building up temperature. And as we had noted, that oftentimes you'll place an isolation pad over the surface of this, because since it's metallic, it's connected to the drain. And that isolation pad will oftentimes have a rather high thermal resistance. And to help make good thermal contact with everything, you'll oftentimes place some kind of thermal compound on the surface of the pad on either side. This facilitates heat transfer by maximizing the surface areas. It will fill in all the little divots and microscopic dents that you have in your material. Moving down here, we can see what an actual heat sink looks like. And so this is a heat sink on one of our boards in the lab. It's got that same MOSFET that was up here is now down here, and you can see we're using just a simple screw or bolt to connect it through. And so this is the front side, and here you can see the back side of the heat sink and the nut that's holding the bolt on. So in practice, this is what it actually looks like. You can go to DigiKey and you can pick out these heat sinks. You can pick out your thermal compound, and of course your MOSFETs. We've already had some practice doing that. Now let's start to talk about some analysis here. And we'd previously noted when we went through a data sheet that for a MOSFET that we had observed a quantity called R theta JC, which was in units of degrees Celsius per watt. And this was the junction to case thermal resistance. And so this is telling us that if we have some loss in our semiconductor junction, that if we are conducting that heat loss through our case to the isolation pad in the heatsink, we're going to have a temperature increase of some number of degrees Celsius per watt of power that's flowing out through our junction. And in the data sheet that we had looked at, we had seen that we had a value of about 5.8 degrees Celsius per watt. The second quantity that we saw was a value called R theta JA, also in degrees Celsius per watt, and this was the junction to ambient thermal resistance. And this is the number of degrees heat rise in your junction when you have your heat be conducted directly from the junction into ambient. So if you have no heat sink on, this will tell you how many degrees Celsius per watt of temperature rise you'll have on your junction as a function of the amount of power dissipated. And so we had noted a value for this, and it was much higher than the junction to case of 62.5 degrees Celsius per watt for this particular MOSFET. And so this is common. Of course, we would expect that if we don't use a heat sink, we're going to have a much greater temperature rise in our junction as compared to when we do use a heat sink. So obviously the heat sink is going to help us get heat off of that junction with a lower temperature increase. So how do we use these thermal resistances? Well, it turns out that we can model a thermal circuit as an analog to an electric circuit. And since we're electrical engineers and we really like circuits, we're very happy to do this. It's something that we know and understand. And I should lead into this with one major caveat that this is a very crude approximation of a very complex phenomena of heat transfer. But this is the common approach that's used in circuit design. So what we do is we convert voltages in our circuit into temperatures. We convert currents into power flows. And resistance is our thermal resistance values. So let's consider an example now. And we're going to consider the simplest case, which is where we're going to take this actual MOSFET that we've been discussing from our previous lecture, and we're just going to consider that we have it operating near its rated point, at which point RDS on was 20 milliohms, and we have 20 amps of DC current flowing in our drain, which is approximately the rated current, and that we have an ambient temperature of 25 degrees Celsius. So TA is ambient temperature. The ambient temperature means our room temperature, or the temperature that our circuit is operating in. And 25 degrees Celsius is approximately 70 Fahrenheit. And finally, we're going to assume that we have no heat sink. So our only conduction path for heat is through the junction to ambient pathway. And so we can study this by considering the equivalent circuit where we have a current source for the power dissipated. This is the total power dissipated in our junction. We have a resistance, which is our thermal resistance of junction to ambient. We're not using the junction to case path because we have no heat sink attached. And then we provide a voltage source over here, which is our ambient temperature. So if we were to measure the voltage at this node right here with respect to our common, this is the junction temperature, whereas this node with respect to common is our ambient temperature. Okay, so I'd like us to work through this example. What I want you to do is I want you to calculate the power dissipated and the junction temperature by solving this circuit. So immediately you know what R theta JA is, because we gave it up above. It's 62.5 degrees Celsius per watt. So first find PD, then find the junction temperature. And hit play when you're ready to see the solution. So our power dissipated is going to be our I squared R losses, so 20 amps squared times our RDS on value, which is 20 milliohms, is going to equal about 8 watts. Our junction temperature, so that's right here, we have 8 watts. And our theta JA is 62.5 degrees Celsius per watt. And our ambient temperature is 25 degrees Celsius. And we're now ready to calculate our junction temperature by solving the circuit. So we have a current source of 8 watts, or a power source of 8 watts, and an ambient temperature of 25 degrees Celsius, which gives us an equation like this for the junction temperature. So that's the voltage at this node. And if we solve this, we find out that we have a temperature of approximately 525 degrees Celsius, which is way too hot. The rated, the maximum junction temperature that the data sheet specifies is approximately 150 volts Celsius. So clearly we are going to melt this device even though we are flowing the rated current, or actually slightly below the rated current. And the reason for that is that we did not use a heat sink. So if we did not put a heat sink on this device and we flow the rated current, we will destroy it. Let's now talk about heat sink selection. In practical designs, you will use a heat sink, and the heat sink is going to have its own thermal resistance of sink to ambient. And between the heat sink and the case, you'll typically have this isolation pad and perhaps some thermal compound. And that's going to give you a thermal impedance of R theta case to sink, R theta CS. And then of course we're going to be using the case of the MOSFET to extract the heat. So you have a junction to case thermal impedance that you have to consider. If we sketch the complete thermal analog circuit for this, we're going to end up with a circuit that looks like this. So we've got our power dissipated, just like before, only now we have several thermal resistances. The first one is going to be our junction to case impedance. The second one, after that, we will have a case to sink impedance. And after that, we're going to have a sink to ambient impedance. And finally, we have our ambient temperature, just as before. And we can label voltage at our various nodes, our temperature at our various nodes. So the first node, again, is going to be the junction temperature. Next, we're going to have a node here, which is going to be our case temperature. And then we'll have a node here, which is going to be our sink temperature. And then finally, we have, of course, our ambient temperature. So if you know the value for all these thermal resistances, and you know your power dissipated, you can solve this circuit to determine the temperature at every point in your system. You can find the junction temperature, the case temperature, the sink temperature, and you already know the ambient temperature. And when you're thinking about this from a design perspective, you perform the following steps. First, you've selected your device already, and so you inspect the datasheet, and you make a calculation for the total power that's going to be dissipated in the junction. And this is going to be the sum of switching losses and conduction losses. Second, you go back to the datasheet and you use the value of your junction to case thermal impedance and your design spec for an ambient temperature to determine what you need for R theta case to sink and R theta sink to ambient. And then you go use DigiKey and you select a heat sink that is within that maximum value, an isolation pad, and probably thermal paste. To summarize, in this video we have introduced an approach to study the thermal behavior of a semiconductor device connected to a heat sink and an isolation pad. We've talked about techniques to use to design the system and select your components. This is a simplistic approach that is workable for the approximate knowledge we have of a design that we are conducting for a power electronic converter. Finally, we're going to take a quick look at a datasheet for an actual heatsink. This is a datasheet that I'm going to post up on the Canvas website. And you can see here that we have a heatsink that is able to work on a TO220 package, as well as a TO218 and a TO247. There's different variants down when you look lower on the datasheet. You can see there's a collection of part numbers, and for each part number is indicated which package or device it can work on. So when we go back up, we see a picture of what the actual heatsink looks like, and we notice that it is secured to the FET via a retaining clip that applies pressure to keep the surfaces in close contact. The key piece of information that I want to point you to is this graph right here. At first pass, this is a complicated graph because it's showing two quantities at once. It's plotting the heat dissipated against the mounting surface temperature, and it's also plotting the air velocity. This is the velocity of air in the environment that the heatsink is placed against the thermal resistance. And so the quantity that we actually care about is the later. That is the air velocity versus the thermal resistance. And these lines that are graphed here, you see how there's an arrow here pointing down. That means that this line is corresponding to this label and this label, which is not the quantity that we care about. Rather, we care about these lines that start on the right side and go to the left. So the arrows here point to this, and they point to this. And so you can see that we get different thermal resistance values based on the conditions that we're using our heatsink in. So if we have forced air cooling, if we have a very high air flow rate, you can see that we're going to get very low sink to ambient thermal resistance values. Whereas if we have very little airflow or even no airflow, we can extend these trend lines up to a case where we have no airflow. You can see that our thermal resistance is much higher. So this is a quick overview of what the datasheet for an actual heatsink looks like and how you can determine the sink to ambient thermal resistance for use in your own designs.